Hello, everyone. Thank you so much for joining today's presentation. I am Mike McCumber. I'm a marketing manager here at DigiFabster, and I'm joined by Michael Stoy, who is an application engineer and will be doing today's event. We're going to dig into machine setup in DigiFabster. So very exciting topic. You do have the ability to ask questions. So what we'll do is handle questions via the chat. So just enter in the lower right-hand corner, you should see a chat function. So enter your question in there. At the end, we'll read those questions aloud and then have Michael answer them so everybody can hear the answers and benefit from the knowledge. But with that, enjoy today's broadcast, and I'll hand it over to Michael.
Thank you, Mike. Hello, everyone. And today what we'll be doing is we'll be going through creating some machines, and we'll be talking about best practices and giving you that starting pricing algorithm. Every single shop handles pricing differently, so these numbers aren't set in stone. And also, again, depending on the machines that you're using and your specialty, these prices definitely can vary. But this should be able to give you that great starting off point, so you can then go in and modify some prices and create that matching algorithm for you. What we'll start off by doing is we'll create a CNC machine, then we'll focus on an industrial level FDM machine, then we can finish up on an MJF machine. So to begin with this, what we can do is we can go to machines and materials. We can then go over to our CNC section, and then we can click create a new CNC machine. This is your first time looking at our CNC module. We break up our CNC technologies into 4 different categories. We have our 3-axis milling, multi-axis milling, turning, and then CNC cutting. So CNC cutting is similar to that of if we had a laser cutter, water jet, or plasma cutter. In this case, we can set up multi-axis milling. From here, we can choose a list of common industry machines, but if we have a different machine, we can always create your own custom machine as well. In this case, I can just choose a Haas. We automatically added in the travel distance. So with this is the built envelope of the part. If we want to have different pricing algorithms depending on the size of the part, what we can do is we can split up this machine by decreasing the full build envelope and increasing the minimum part size. This way we can price very small parts differently than medium-sized parts, differently than large-sized parts. Now we'll open up our complexity bracketing. How the complexity bracketing works is whenever a part is uploaded, we'll automatically analyze the part and see how complex it is to machine. We then apply each part into a different bin, from very simple all the way up to highly complex. We can then create cycle time multipliers to account for how each shop machines these different complex parts. If a shop is very proficient at machining highly complex parts, they can decrease the cycle time multiplier, and if they're very proficient at very simple parts, they can then decrease that simple cycle time multiplier. A typical multiplier setup will be something around 1.1 for very simple, and then ascending all the way up typically to around 6 for the highly complex. Again, what we highly recommend is start off with some baseline settings, test it with some complex and highly complex parts, and then what we can always do is we can always come back and fully modify the pricing. With DigiFabster, it's very flexible always to go back and change values. So again, we highly recommend starting off with these base values, and then we can take a look and say, this value is high, this value is low, and modify it. Another great example of that is the machine speed. This is based on physical properties of your machine. However, we recommend starting off with 1,000 as a great baseline. And then what we can do is we can always tailor that to better fit our speeds when we actually start testing with real models. We can set our hourly rate. And in this case, we can set that to be something like $100 per hour. If we choose to, we can have a per part fee. And this per part fee will be accounted for any type of handling of the materials prior to machining, or maybe even offloading the parts after machining. So we can throw in something like a $10 per part fee. Inside of our CNC module, we also have the ability to hold large orders for review. So if someone's ordering 10,000 of a part, we can hold that order for review. In this case, what we can do is we can just set that to be 100 pieces. Inside of our CNC module, we allow customers the ability to choose different tolerance options. So what we can do is we can have a high tolerance option, and what we can do is we can have an additional margin on the part. So we can say there's a 25% margin for having a tighter tolerance. Other shops prefer to have a set of base tolerances for their shop, And then what customers can do is they can choose the base tolerance with 1 or 2 advanced features or high tolerance features. This way, again, we can have that baseline set up, but if there's one feature that's very critical to the part, we can have a higher tolerance feature for that one part only. Speaking of features, we have feature recognition. So what we can do is we can have feature recognition cost for a hole in a part. We can choose to look on different faces of the part. So we can look on axial radial parts, or we can look on any cuboid face. In this case, we can have a price per feature of something like $2 per part, maybe a $10 startup cost. Finally, we can get to our lead times. With our lead times, we have the ability to create multiple different lead times with different margins to upsell customers. So if we need this part much quicker, we can have a 5-day rush lead time with an additional 20% margin. It's a great way to upsell customers if they ever need a faster turnaround time. We can now save the machine and we can create a material. By default, we have a list of common machining metals, but if you are using a custom material or a special alloy, you can always add your own additional material. In this example, what we can do is we can choose aluminum. If we want to, we can change the display name, and this is what's shown to users. So in this case, we can just name it as aluminum. You can also add notes and a material spec sheet for the user as well. Now, when it comes to the CNC space, we have 2 different costs that we can set up as a flat cost. We can have the startup cost, which can be applied for every unique material. So if we needed to change out all of our tooling to work with titanium or some other complex metal, what we can do is we can have a startup cost applied for that metal. We also have the programming cost, and the programming cost is assigned with every unique part. So in this case, we can have a $100 programming cost for every unique model. In our CNC space, if we wanted to add in cost for 1-offs or 2-offs of parts, we can add this off in 1-off costs. So it has the customers buying one part, the price will increase, but this cost will then be spread out among as many parts as they have. So if a customer is ordering 100 parts or 1,000 parts, these 1-off costs will become almost negligible in the final pricing. Next, we have our material specs. With this, we can have a minimal mold thickness along with our machinability rate. And the machinability rate is how we can account for the different machining speeds of different materials. By default, we have all of these tabulated in our system. But again, if we're very proficient at aluminum, we can always go in and manually change this to machinability rate of 200. The other one that we always like to point out is our extra material added to the bounding box. And this is how we're able to determine our bar stocks or other ways that we can account for the material needed for the part. Speaking of the material needed for each part, we can get to our material costs. What we can do is we can set up in bar stock sizes, round stocks, or price per kilogram. What we highly recommend is working off a price per kilogram for common materials, such as aluminum and steels. And then if we're working with more expensive materials or more complex materials, that's when we recommend working in bar stocks. But since aluminum's the material cost is relatively low compared to the machining cost, in this case we can just set the density and then we can set our price per kilogram of something like $12 per kilogram. Finally, we can get to our post-production type. With our post-production type, we can choose to add different metrics. So with this, for polishing, for example, we recommend charging off the model surface area. And again, depending on shop, we can recommend something around 12 cents per square centimeter. We can then save our material. And just like that, we've set up our first CNC machine. Now what we'll do is we'll do a very similar approach, but what we'll do is we'll create an FDM machine. And one of the things that is interesting about FDM technology is that it varies greatly. So they have $200 machines, they have $200,000 machines. And the pricing will vary a lot more compared to a CNC or other technologies out there. In this case, we'll create an industrial machine. So in this case, we can create a Stratasys 450. However, for industrial machines, we can use a similar pricing algorithm. However, there always will be some slight changes from different machine to machine, or even each shop's different pricing algorithms. Similarly to our CNC space, we have our printer size. And again, if we wanted to charge different prices for very small parts compared to medium size or large size parts, we can account for that as well. And we can use that by using our printer size and our minimum part size as well. Now we can get to our machine specs. So with this, we can set our horizontal print speed to be 165 millimeters per second, And what we can do is we can charge something like $20 per hour per part. If we wanted to have a per part handling fee, we can again have something like $10, $20 per part. Now we can get to our geometry. Typically with FDM, we recommend bypassing this. However, if we choose to print with very thick walls or other modifications compared to a default slicer, what we can always do is we can add additional cost per surface area, per the surface area bounding box, so that's the XY plane that the part takes up, or even per the bounding box of the part. Some of our customers who are using something similar to a metal printer, who are then sintering parts afterwards, will use this to account for the materials or volume that the part takes up inside of a kiln or sintering oven. Next, we have our lead times again. And with this, again, we can always create a rush lead time with an additional margin as well. We can then save our printer. And now what we can do is we can create a material. So by default, we have a list of common materials for each machine. However, if you want to use a custom one, you can always change that. You can also, again, change the display name, add notes, and a material spec sheet as well, so customers are fully informed about what material they're selecting. When it comes to 3D printing, we highly recommend working off a price per gram of material. And with this, we'll automatically determine how much material will be used depending on the density. So we can have that be 1.07, and we can have our price per gram of material be something around 20 cents per cubic centimeter, or per gram of material. If we wanted to work off of volume, we can leave the density as 1, and then we can be working off of cubic centimeters directly. We also have material limits. So with this, we can set a minimum wall thickness, minimum hole thickness, and also a level of support. Typically with the Stratasys systems, there's something around 18% support. With our support, we can have this be printed in a different material. So if we were to have a water-soluble support or another type of support, we can have a different density and a different cost per gram of support. So we can have something like 30 cents. With our FDM pricing, if you choose to, we can have price mutations. And with this, we'll have an exponential curve. So as the parts get larger, the price per gram or price per bounding box decreases. This is a great way to decrease the price for these larger prints and incentivize customers to order those. With printing as well, we also have the ability to give customers different layer thicknesses and different infills. And this will prompt users and allow them to choose which options are best for them. So we can have a 254 micron option, and we can also have a 126. So again, customers will be able to choose between the two different options. We can also have different filling options. So we can have 100% solid. We can also have something like a hollow part with, again, that 18% infill. Depending on your clientele, if colors are important, we can offer different colors. However, if we're working industrially, most of the time we only offer one color of a white, for example. And then similarly to our CNC, if we wanted to offer any other post-production options, we can provide those as well. So what we can do is we can offer sanding of parts, for example. We can again choose to charge off the model surface area, volume, bounding box, or just a per part fee. And with this, we can set up something so it's like 15 cents per square centimeter, and we can have a minimum price maybe be $10 per model. Then what we can do is we can save our material, and just like that, we set up an FDM machine. Finally, we'll set up an MJF machine. One of the benefits of MJF technology is that it's very close source, and a lot of the shops are using very similar setups with very similar materials. There's a lot less variation depending from compared to FDM or even CNC technology. So what we can do is we can select MJF, and then we can select one of our default printers, or if we're using a different one, we can always create a custom printer. In this case, I can select a 4200. We can automatically add in the printer size along with the minimum part size, similar to FDM and CNC. Inside of the MJF setting, we can also set a nominal growth rate, nominal fusing rate, nominal layer thickness, and a price per hour and a per part fee. However, when it comes to MJF, we're typically printing multiple parts at a time. So for this case, we recommend staying away from this per part hour unless we're printing very large parts. So again, this is a case of we can use this pricing algorithm for giant parts, but for all parts that we're going to be batching and nesting together, we can use a different pricing algorithm. For these different pricing algorithms, we recommend first working off of the volume bounding box. This accounts for how much volume and how much space the part takes up inside of the build's volume. This is a great example of, think of if we were to be printing a bird cage. So it takes up a lot of space, but it's very low volume. There's a very high opportunity cost for printing that part, so we recommend having in a cost for volume bounding box. In this case, a typical price for this is typically around 4 cents per cubic centimeter. The other cost we recommend putting in is a price per surface area. So if you're not familiar with MJF pricing, what happens is we have a detailing agent applied to the outside of the part. This allows for cleaner and sharper lines. However, we also want to account for that by adding in a cost per surface area. Again, we can then go to and add lead times, or we can just continue and save our machine. With the MJF system, most shops only offer PA12, but if you wanted to offer PA11 or other materials, you can also add those as well. When it comes to printing the parts themselves, a lot of shops will only offer fully solid parts, but if you wanted to hollow out parts, we could also offer that as well. In this case, since we are offering only solid parts, what we can do is we can just charge per model volume, and with this, we can charge something around 20 cents per cubic centimeter. We can again also change that minimum wall thickness and minimum hole thickness. And then this is the case where we highly recommend adding in that bounding box exponent. This is a great way that we can incentivize customers to order larger parts. And at the end of the day, we highly recommend trying to get larger parts and larger orders from customers. It's much more efficient to be printing 1 or 2 large parts as opposed to 50 small parts. So in this case, what we can do is we can set up an exponential value of something like 0.85. The layer thickness on the MJF machines is fixed at 80 microns, so you can just display that to end users. And with this, end users will then be able to compare maybe MJF or FDM to choose what's the right technology for them. Or if you choose to, we can also disable this showing from the e-commerce widget, so it can be as streamlined as possible. Again, if we wanted to offer hollowing of models, we can account for that as well. And then we can also add for post-production. So if we wanted to offer dyeing of parts, what we can do is we can choose to charge off model surface area or model volume. And with this, what we can do is we can charge something like 5 cents to dye the parts, and we can dye them black and a dark gray. So we can then display the colors, so this way customers know exactly what they're ordering. Just like that, we can save our material. And then we've just set up our first 3 machines. At this point, does anyone have any questions? Or is there anything else that we can dive into showing about how we can efficiently set up machines?
Yeah, so Michael, we do actually have one question that I see as of now. It is, what input is necessary for an accurate pricing algorithm?
That's a great question. So there are a lot of different ways to assign cost of manufacturing, and every single shop will handle it differently. A good pricing algorithm, though, will look at the material costs, obviously. So what is this costing in material, in labor, but also another one that some of our shops fail to look at is the opportunity cost. So again, if we're printing a bird cage that's taking up our entire build envelope, so it's going to take us 8 hours to make this part, even though it's low volume, that should have a much higher cost associated with it. So the big things again to look at are the fixed costs of the material, the labor involved of removing the parts, cleaning up the parts, but also on top of that, we also need to look at the true cost of what is this costing to print. Instead of printing this, could I be printing X, Y, or Z and having a much higher return on investment? So a good pricing algorithm will look into all of those, and what we'll be able to do is be able to assign costs so we're never losing money. And the big goal of a pricing algorithm is to make it so there are no edge cases in which a shop can potentially be losing money or be losing time when they could be printing much more economical parts. And if you have any questions about what are maybe some edge cases for different technologies, feel free to reach out after this call. We have a small library of parts that are edge cases that we can demonstrate of maybe printing one way or the other might not be the best way to price your parts.
That's great. give another couple seconds here. Again, if you do have any questions, feel free to ask them via the chat. Enter that in, and we will. We do have another question. Does the software do slicer run to base the cost and relative amounts of material versus support material?
Yes, so we have a built-in slicer internally that we use for FDM. And with that, we automatically analyze a part. And when we do, we'll also analyze how much support is needed. So we can go and get a cost breakdown of this part. And I can choose a Fortis machine for this example. Inside of this part, in our cost breakdown, we can see the actual gram usage of the main material along with that support material. So we give shops, if they want to, we can analyze and say, in this orientation, we'll need support for these 3 small holes. This will come out to this amount of support material. So we do analyze not only the main material, but support material. And also if we were to have a very long part or something where it needs lots of travel distance, we also can account for that as well.
Great. All right. Any other questions? We'll give it another couple seconds here. All right, here we go. How does it figure out orientation for the slicer?
So we give shops the ability to set orientation rules. So if we want parts laying down, standing vertically, or other rules associated with that. So it's up to the shop to define how they prefer parts to be printed. So a great example of that is SLS or even SLA technologies, where some shops are trying to print parts flat, other shops are preferring to print at 45-degree angles to minimize layer lines. So it's up to the shop to define and choose which orientation they prefer the most, and then they can reach out to us and we can configure that in our backend. So this way, whenever a part's uploaded, we'll automatically orient it into that orientation, and will allow the customer then to get the price based on that orientation. And if there's additional supports needed, we can account for that as well.
All right. Just another couple seconds, but just a reminder, if well, a few things, I guess. We'll be sending out a recording of this so you can rewatch, and if any other questions do come up, feel free to reach out to us and we can answer those via email, or yeah, just get back to you with whatever questions you may have after this session wraps up. All right, Michael. Well, I don't see any additional questions right now. So thank you all again for attending. You will get an email of the recording of the session here, and remember that we do this monthly, so stay tuned in our social media feed, and of course we always send out an email invite as well to register for these webinars. So thank you again, everybody. Have a great week, and good luck out there.
And also, if we don't see you until next year, hope you have a great new year. See you next year.